For the second last talk, it's a great pleasure to introduce Professor Ben Woods to you, who's a center here and has great expertise, actually, beyond this, also in topological quantum information related systems. He'll speak about the theory part, counterpart to what Mark showed in the previous.
All right, thanks. All right, thanks everyone. Thanks for coming to the summer school. It's as Hilly was saying, it's the second to last talk, so I hope you all have enough energy and attention left to talk about spin qubits for a while. This is about learning, so please stop me and ask questions the whole time. I would much appreciate it if you get confused or just want to ask a clarifying question or anything. Okay. So I'm going to be talking about largely spin qubits and semiconductor quantum dots, and the goal is to give you kind of the basic nuts and bolts and the operating principles about how these spin qubits work. That's going to be the kind of my first part of the talk. And then the second talk, I'm going to talk a little bit about the value problem that Mark was mentioning in the questions session during the last talk, and about kind of our recent strategy for trying to solve that problem. Right? Okay, so let's see if my pointer works. Sorry. Now my clicker doesn't want to work. 1 second, sorry. There we go. Okay. All right. So, as you saw in Mark's talk, the platform for making these spin qubits are these gate-defined semiconductor quantum dots. And this is a cross-section of one such device, right, where we have some semiconducting material like silicon or germanium. And then around it is a barrier material, typically made of silicon germanium, right? Some silicon germanium alloy. And the electrons that we're going to form our spin qubits out of live in this quantum well region as shown here. And then on top of the stack, we have these metallic gates, right? That we can use to basically tune the electrostatic environment in the semiconductor. And by tuning these voltages properly, we can isolate, a small number of electrons in these regions that we call quantum dots, right? And remarkably, you can control the resolution of the number of electrons that you have in these dots down to the individual electron, right? Just to show that a little bit more clearly, I have a charge stability diagram plot over in the top right here for this device that has 3 plunger gates. These P gates are called plunger gates, and these are the gates under which the quantum dots are defined and the electrons are going to live. And here we're going to just ignore the third one and just look at these 2 dots here. And on this then is showing you basically the charge occupation as a function of the plunger gate voltage of these 2 gates. And you can see if you apply a small enough voltage to these gates, the system is completely depleted. And so there's no electrons underneath either of these quantum dots. But then as you apply voltages, you can trap a select number of electrons underneath these dot regions, right? I mean, indeed, you can see you can get down even to the single electron level, right? So a single electron resolution. In addition to these plunger gates, we also have barrier gates in the device to control basically the coupling between these quantum dots, right? And also to the reservoirs as shown here. To give you a sense of the length scale, there's a length scale shown here. And roughly the distance between these gates or the quantum dots is around 100 nanometers. And the electrons underneath the dots are localized on a length scale of around 10 to tens of nanometers, okay? And then, this is a very exciting time to be in this field because, like Mark was saying, there's now becoming larger and larger arrays that are becoming available. So just for a long time, we were kind of stuck with just a handful of dots, right? Which you could still do fun science on, but we're limited. And now you're starting to see more and more of these 2-dimensional dots. So, for example, this is a view of a 10-dot device, actually, with germanium holes out at Delft. That was published just last year in Science. And as Mark was saying too, now Intel and HRL and these larger companies are showing devices that up to have like 50 to 100 quantum dots, right? Where you can start to envision exciting things. Okay, so this is kind of a table of the different types of spin qubits you can have, all the different variety. I call it the zoo. Mark told you that there were 4. That was a lie. There's actually many more than 4. There's more than 4 types. And this just to give you a sense that there's actually a very rich playground to look at in terms of thinking about different ways of encoding information in these quantum dot systems. We're going to focus largely on the simplest one up here, this lost DiVincenzo qubit, which is just a single spin inside of a single dot, right? But we'll also touch upon a single triplet qubit, which corresponds to having 2 electrons, so 2 spins in 2 quantum dots. Right? And we'll just see how by adding electrons to the system, that gives you a different encoding to your quantum information and allows you to control the qubit in a different manner than for this, this simple lost DiVincenzo qubit. Okay. And if you're interested in this type of thing, if this thing interests you, you should really look at this great review article that came out a couple years ago in Reviews of Modern Physics. It's a great review article about spin qubits. Okay, and I highly recommend it. Okay, so even before talking about spin qubits, I think it's actually motivating to talk about a different type of qubit that you can define in these gate-defined semiconductor quantum dots. And this is namely charged qubits, right? Where we're not going to encode our quantum information with spin states, but rather in charged degrees of freedom, right? So for that, we'd like to think of some double dot system as shown here, right? Where we have these 2 plunger gates from which we're going to define quantum dots. And then we could have a barrier gate, right? That can control the coupling basically between these quantum dot regions. And just I'm showing here is an example double dot potential as a function of X. Okay. Now, and I should add here, for this simple charge qubit, we're just going to have a single electron in the system. Okay. Even though there's 2 dots, we're going to still add just 1 electron that can hop back and forth between these dots. Now, if we have strong confinement in these quantum dot regions, we only really need to consider a single orbital per dot, right? So these could look something like this, right? Where the charge is either going to be localized in the left dot, which I denote here as L, and then, or it could be localized in the right dot, which I denote as R, right? And these are then a charge degree of freedom because it's about where the electron's charge lives, right? Okay, and so you can recognize that this is then a 2-level system, right? Because it's a Hilbert space with just 2 basis states. So if it's a 2-level system, what is this thing? Sorry? It's a qubit, right? Because like we were saying before, any 2-level system that you could think of, in principle, can be made a qubit, okay? So this is going to be the basis states for our charge qubit. Now, of course, that the most generic state is not going to be just the left or right charge state, but rather it can be a superposition of these 2 states, right? Which I've written here in kind of the block sphere representation. This is the block sphere of our qubit. This is really a very powerful visual tool to understand any qubit, right? So whenever you think about a qubit, you should always really have this block sphere picture in mind, okay? And what this is it parameterizing all the generic qubit states that we can have, where we have some polar angle theta, right? Which is telling us basically that the magnitude of the mixture of the superposition between these left and right charge states. And then you have an azimuthal angle phi, which is going to give you the relative phase between these charge states. So on our block sphere, right, we have our computational states 0 and 1 at the poles of the block sphere, which correspond in this case to the left charge state and the right charge state. And then when you go away from the poles, right, as theta becomes 0 or not pi, then you get a mixture of these left and right charge states. And at the equator, it's a perfect superposition, right, an equal superposition of the left and right. And then the angle is going to tell us, right, the relative phase between these charge states. Okay, so let's suppose then that I start in some superposition state shown here, right? And we can then ask, how is our charge qubit going to evolve in time? Okay, and for that, we need to think about the system's Hamiltonian, yeah? The Hamiltonian, of course, tells you the time dynamics of how your system will evolve. Now, in this case, it's very simple, right? Because it's just a 2-level system. And so it's just a 2x2 Hamiltonian, right? So it's nothing scary. So let's just break this down. On the diagonals, these are going to be the energy expectation values for our charge states, right? Our left and right charge states. And these can be controlled via the plunger gate voltages, right? By just tuning the electrostatic potential that each dot feels, I should be able to control these diagonal elements, right? And it's very useful to then define a dot detuning parameter epsilon, right? Which is just basically the difference between this left charge state's energy expectation value and the right charge state's energy expectation value, right? And intuitively, it's just about, how much is this double dot being tilted by the gate voltages that we apply. Okay, now classically, if the system behaved classically, that would kind of be it, right? But we know that the electron can also tunnel through this tunnel barrier, right? And this gives rise to what's called a tunnel coupling between these two charge states, okay? So this is going to be the off-diagonal coupling between the left and right charge states. And so it shows up on the off-diagonal here, TC, and yeah, I said we call this the tunnel coupling. Okay, so this is then our basic Hamiltonian for the charge qubit. You have the charge detuning on the diagonal, and then the tunnel coupling that can mix these two states. Okay, so then we can ask, well, given this, how is the system going to evolve? And it's very useful then to think about kind of some limiting cases. Okay, so in the limiting case, when the charge detuning is very large compared to the tunnel coupling, right? Well, you can basically forget about the tunnel coupling in that case, right? And the eigenstates are going to be just the left and right charge states of our system, right? And they'll differ just by an energy of epsilon, okay? So because of this, the left and right charge states will accumulate phase at a different rate, right? Because they have different energy eigenvalues. And because of this, it's going to cause Larmor precession for our spin qubit, right? About the z-axis, right? It's going to, if we started here, it will go about the z-axis like so, right? And again, it's just because the right charge state is accumulating phase as time passes due to this charge detuning shown here. Okay, so that's how you do single qubit gates for a Z gate. Yeah. Now you have to think about, well, how do I do X gates, right? How do I do rotations about the X axis of my qubit? Well, if we think about the case when the detuning is 0, right? Then all we're left with is the tunnel coupling on the off diagonal of our Hamiltonian, right? And then the eigenstates of the system are not the charge states themselves, but are what? I just have the tunnel coupling. Where my eigenstate's going to be? Anyone? Owen? John, go ahead.
Like the maximum.
So there should be equal superpositions between the left and right, right? So there should be the plus and minus of those guys, right? Exactly. And so because of that, you don't get Larmor oscillations about the z-axis, but rather about the x-axis, right? Because we have the quantization axis, if you just have TC, is along this x-axis of our charge qubit, right? Okay, so now you can see that by changing the detuning, I can go from having Larmor oscillations about the z-axis down to the x-axis, right? And this is called having two-axis control. And this is basically universal then for making any single qubit gate that you want, right? You can decompose any single qubit gate as a combination of these, elementary X and Z gates by just taking the appropriate combinations of the two of them. And so this is all you need to completely control a single qubit, okay? All right, so having now kind of talked about the operational principles of a charge qubit, we can think about why might this qubit not perform very well? Anyone have any ideas about why this might be a not so great qubit? You can ask what would cause a fluctuation in these parameters for my Hamiltonian? Anyone have any ideas? So remember, these are coming from tuning the electrostatic environment, right? And so if I have, oh, go ahead. Right, any sort of fluctuation in the electrostatic fields, right, are going to cause these guys to fluctuate as well, right? So if I have charge traps, for example, at the interface between my semiconductor and oxide, right, which we know there are, and they're jumping around, right, they're going to be causing fluctuations in the electrostatic environment. And in turn, that's going to cause a fluctuation in these detuning parameters, right? So there'll be the epsilon will not be exactly what I think it is, but rather it will be epsilon plus, delta epsilon, a small little value. And that's bad for our qubit, right? Because think about what that does. If I change epsilon by a small amount, that's going to now cause the phase to accrue at a different rate, right? And the phase then becomes uncertain to me. I'm not going to know anymore what the phase of my qubit is, right? And this is a type of decoherence that we call dephasing, right? And so that's why charge qubits are bad in terms of semiconductor quantum dots, because they couple directly to the charge noise, right? And any little sort of electrostatic fluctuation is going to cause an energy splitting that changes and give me dephasing, okay? And this is what then motivates us to think about the spin degree of freedom, right? Because the first approximation, the spin degree of freedom doesn't couple to such fluctuations, okay? All right, so now that we've talked about the charge qubit and motivated for thinking about the spin qubit, let's then dive into thinking about the single or simple type of spin qubit, known as a lost DiVincenzo qubit. It's named this because of, as Mark told you guys, it's from the guys who proposed this back in, I guess, 1996. I thought it was 2000. So I was going to say I was in kindergarten, but now I can say I was 2 years old when this was proposed. Many of you probably were not alive yet, right? So that's always fun. All right, anyway, so let's talk about this single spin qubit. All right, so here then we have just a single quantum dot, right? And instead of having a charge degree of freedom in co.qubit, we'll have the spin up and down BR0 and 1 state, okay? And here there's nothing yet, so they're completely spin degenerate, right? Now, analogous to how I had the detuning in my charge qubit give rise to a qubit splitting, right? I need to also provide a single qubit splitting here as well, right? Between my states. And how can we do that? How could we get a splitting? What causes spins to split? Yeah, go ahead. The magnetic field, right? That will cause a Zeeman splitting. So if we apply some static magnetic field, right, that will split our states like that, and there'll be a Zeeman splitting that's proportional to this magnetic field. Okay. Now we should think about this. Then again, I said we should always be thinking about qubits in this block sphere representation, right? And so now the 0 and 1 computational states just are going to correspond to our plus and minus states, right? And now we can think about, well, let's suppose I just have my Zeeman Hamiltonian, right? I just have my applied magnetic field to the system. We're going to have a very simple Hamiltonian that just gives rise to a Zeeman splitting, right? Or EZ is the Zeeman splitting, and poly Z is the third, poly matrix, right? It's just the off diagonal. It's just 1 and minus 1. That's all this is, right? In the spin basis. Okay. So what is this thing going to do to our qubit state if I just put a magnetic field there? How will this qubit state evolve in time? Anyone? So in this case, the spin up and the spin down are the eigenstates of the system, correct? And so they'll accrue phase at different rates, right? Because they have different energies. And when you are accruing phase, that means you're going to be going around the block sphere like that, right? So this Zeeman splitting is going to be providing us with these Larmor oscillations about the z-axis as shown here, okay? Just like how our detuning in our charge qubit gave rise to these z-axis Larmor oscillations. Okay, so then you can ask, well, great, I can rotate my qubit around the z-axis, but now how do we perform a rotation about the x-axis? How do we do an x single qubit gate, right? So in principle, what you could do is you could take this magnetic field that you've applied and you could rotate it, right? And that would change the quantization axis from being along z to being along some different axis. But practically that will never work because it takes a very long time to change the magnetic field in these experiments, at least compared to the qubits, the time scales of a qubit, right? And so we're kind of stuck with this static magnetic field pointing in one direction. And so another thing that you can do, though, is apply an oscillating field in an orthogonal direction, right? This is going to be the basic Rabi driving for our spin qubit. So if you apply, say, a B field B prime in the orthogonal direction, and we're going to oscillate it with some omega, frequency omega, shown here. Now our lost DiVincenzo spin qubit has a Hamiltonian like this, right, where our static magnetic field is giving rise to their splitting. And then we have this driving term on the off-diagonal elements of our spin qubit, right, as shown here. Now, hopefully, many of you will hopefully recognize this as just being the Rabi Hamiltonian from elementary quantum mechanics. And if you drive this thing at what's called the resonance frequency, right? So it's basically the energy splitting coming from the bare static magnetic field that you're applying, divided by h bar. If you drive it at that rate, the spin will undergo what's called Rabi oscillations, right? And will process about the x-axis now with a frequency known as the Rabi frequency that's going to be proportional to this applied oscillating magnetic field. Now, what I should say here is that this oscillating magnetic field is typically much weaker, right, than the static one. And so what you're doing with your quantization axis is essentially wiggling it back and forth, right? And so this Rabi frequency, correspondingly, is going to be much smaller than the Larmor oscillation frequency set by just the bare static Siemens splitting. Okay, so then, the next obvious question to ask is, well, how do you realize this oscillating magnetic field? Yeah. Well, there's one way to do it. It's kind of straightforward. Is to put a big antenna next to all these quantum dots, and you drive an AC current through it, right? Which is shown here from a recent Nature paper out of a company called the RAC in Australia. And when you do this, driving the AC magnetic field, when you drive this AC electric field, that's going to cause an AC magnetic field, right? Just by the usual Biot-Savart law or whatever of E&M that you learned when you were a sophomore or whatever it was. Right? Okay, so this is one way of doing it, and there are groups that are pursuing this in the world, but it has some difficulties, right? You can see that this antenna, it's huge compared to the other components of the spin qubit device, right? And in fact, it's much bigger than the individual quantum dots. So for example, the individual quantum dot is defined in these little regions here. And so if you try and put this microwave antenna here and you drive it, you're going to be correspondingly producing oscillating fields that go across this entire array. Yeah. And if you're trying to selectively drive individual qubits, that makes it difficult, right? Because they're all feeling the same oscillating magnetic field. And so that's one difficulty that you have to deal with. And secondly, this produces a quite small magnetic field that you can get. And so that correspondingly limits the Rabi oscillations. So this is not, I would say, the main way that people do this for most spin qubit schemes. The most popular way, actually Mark started talking about it at the end of his talk, is using a micromagnet. Okay, and this is what I would call electric dipole spin resonance with what's called synthetic spin orbit coupling. Okay, so just to explain what this means, let's just imagine we have our single electron spin qubit, right? And we've applied a magnetic field that gives us some Zeeman splitting shown here. What we can now do is immerse this dot in some inhomogeneous magnetic field by putting a micromagnet nearby. Okay, and because the micromagnet's small, the magnetic field will vary in space. Okay, and so what you get then is a Zeeman Hamiltonian that looks very much like what we had before, but now there's this position dependence to your magnetic field. Okay, and this position dependence is what allows you to couple the orbital motion of the electron to the spin degree of freedom. So just think about this. Imagine that the dot is located at the origin, so r equals 0. And we just expand this magnetic field in some kind of first order, Taylor expansion. Well, there'll be a static component, right, that gives rise to this Zeeman splitting shown here. But then there'll be a first order term that's coming from the gradient of your magnetic field provided by your micromagnet. And what you can see is that now there's a orbital motion, the r of the electron, right, that talks about the position, dotted with the spin degree of freedom, our sigma matrix, right? And this spin orbit coupling then is what allows you to drive these Rabi oscillations. So just imagine, I'm sitting here in my magnetic field that's inhomogeneous. Over here, it's going to be a little weaker. And then over here, it's going to be a little stronger. And so if I jiggle the dot back and forth, right, it's like the electron's experiencing an oscillating magnetic field, right, effectively. And if you do this again at the resonance frequency, this is what can drive Rabi oscillations. Okay. So this is what one of these structures looks like. So under here, what you're seeing, these gates, these are the metallic gates that are defining the quantum dots. So in this particular device, for example, these are the little dot regions where the electrons are localized. And you can see that these micromagnets are huge in comparison, right? Compared to these dot-like structures. Now, they've been incredibly successful. So in just the last couple of years, they now are seeing qubit fidelities that are over 99%, right? Which is kind of the threshold for starting to do error correction. And I should say here too that the 2 qubit gate fidelities are also now over 99%, but just to focus on the single qubit driving. So this is indeed, I would say, the most popular method currently for driving these Rabi oscillations in Laskey-Vincenzo qubits. There are some issues. So they present some scalability issues. As I was saying, they're huge, right, compared to the individual dots themselves. And so when you think about scaling up to, millions of qubits, it's kind of an engineering challenge to think about how you would exactly arrange these things such to get the proper field gradients that you want, right? Another issue is that it also exposes the spin qubit to charge noise. So if you remember, I said that when we were looking at the charge qubit, we had a direct coupling between the qubit's basis states, the left and right charge states, to charge noise in the system. And the whole motivation for looking at spin qubits was that they're not supposed to be perturbed, right, by this electric field noise, at least not nearly as much as the charge noise. But now let's think about why it is that this exposes the spin qubit to charge noise. Okay, so what happens when I take my electron now and it gets shifted in space by a charge fluctuator? What does it experience differently if I move it from here to here? There's a micromagnet, remember? So what is it experiencing differently in the 2 different positions? Yep. Right, exactly. So the magnetic field is different in these 2 locations, right? And so that's going to change our Zeeman splitting, right? And remember that Zeeman splitting is what gives you this Larmor precession, yeah? And if that rate is changing, then this is going to cause dephasing, right? Because if you're uncertain about where you are on the Bloch sphere in terms of the angle, this is exactly what decoherence is, right? This dephasing is. So these micromagnets, while they have been very successful, they also do expose the spin qubit to some charge noise. And I am looking at different ways of trying to mitigate this, but I'm not going to talk about that too much in this talk. If you're interested in that, welcome to talk to me about it. Okay, so we've covered then, single qubit gates. We could then ask, well, how do you perform 2 qubit gates in the system, right? And for that, we need, 2 qubits, which in the case of a Laskey-Vincenzo qubit are going to be 2 single spins, as shown here. So again, we have just our double quantum dot, right? And this is going to be qubit 1, and this is going to be qubit 2, okay? We put it in a magnetic field, so we get our Zeeman splitting, and then we're going to ask, well, how does this thing evolve in time? And to understand that, we have to look at the system's Hamiltonian, okay? So this first term is just the Zeeman splitting caused by this applied magnetic field, right? So we have, poly Z1 and poly Z2, where the 1 and 2 are just denoting, which dot electron I'm talking about. So this one is talking about this one is talking about this one, okay? And this is just defining our Zeeman energy for the 2 individual qubits, okay? But then there's going to be an interaction between these qubits as well. That goes by the name of the exchange interaction, and it's a many-body interaction in nature. But you can boil it down to a form in the Hamiltonian that looks like this, where J is known as the exchange coefficient, and you then have sigma 1 dot sigma 2. Okay, and so classically, the way you can think about this is this term here wants the spins to be anti-aligned, right? Because it will lower the energy. It costs J over 2 energy to have the spins be aligned, right? Classically. Okay. Now, it turns out when you apply quantum mechanics, it's a little bit more than just up and down, right? Because you can have equal superpositions. And so instead of it being just up and down, rather it gives you, I think stopped working again. There we go. It causes splitting between what we call the spin singlet and the spin triplets, right? So hopefully you maybe have seen this also in elementary quantum mechanics, where the spin singlet is going to be the antisymmetric version of the spins, right? You have spin up minus, or spin up, spin down minus the reverse. And then you have these triplets, right, which correspond to being spin ups, and then spin downs, and then up, down, plus down, up, right? You should know that, if there's no magnetic field, then these triplets are going to be completely degenerate, right? And this exchange energy just lowers this spin singlet compared to these two triplets, okay? And what you can show is that this exchange interaction then allows you to swap the two states of the system, the two spins. So if you wait basically a time that's inversely proportional to this exchange interaction, the two spins will swap states, right? So up, down will go to down, up will go to up, down, and then up, up, right? That is exchanging the spins, but it's still the same state. And this is then how you can do, one type of 2-qubit gate. If you wait a fractional amount of time, it will actually produce an entangling gate that will entangle the two spins. And this is then how you can perform 2-qubit gates in Loss-DiVincenzo spin qubits, okay? Now, the physical origin of this exchange interaction is actually quite interesting. So like I was saying, it's a many-body problem that you have to think about. And it comes from the combination of Coulomb interaction and the Pauli exclusion principle, right? Which is kind of amazing. If you think about the Coulomb interaction, right, it doesn't know anything about spins, right? If there's the same Coulomb interaction, whether or not the spins are up and down or up, up, right? It doesn't know anything about it. Yet when you pair this with the Pauli exclusion principle, it then can give rise to this spin-spin interaction, right? And this gives rise to all sorts of interesting magnetic structure and bulk materials and things. But here we're just going to exploit it to do a 2-qubit gate, okay? All right, so that covers the Loss-DiVincenzo spin qubit, okay? Now, one of the main disadvantages of that Loss-DiVincenzo qubit, right, was that in order to do X gates, right, to do rotations about the X axis of our spin qubit, what did we have to do? We had to apply an alternating magnetic field, right? When we applied the micromagnet, we could still do this electrically, right? We just had to jiggle the dot in space, but nonetheless, we do still have to apply some AC signal to the system. And why do you think that might be an issue? What problems could that cause? Anyone have any ideas? I take a bunch of charge and I move it back and forth. What do you think is going to happen to the system? So you're going to go down in temperature or up in temperature? Up in temperature, right? Because you're basically sloshing charge around, right? And the energy of that oscillating signal has to go somewhere, right? And so if you're sloshing charge around, that's going to heat the system up. And then if you're trying to do quantum computing, we need to keep this at very low temperatures to keep the quantum effects around, right? And if you're sloshing charge, heating it up, well, it's bad news, right? So that limits you how fast you can drive with these AC signals, right? So it'd be great if you could make a qubit where you didn't have to do this AC driving, but rather you could just slowly change the gate voltages, right? And that's a large motivation for introducing these different types of spin qubits shown in this table of spin qubits shown here. So just to give you a flavor of that, I'll talk about the next simplest qubit, which is known as a singlet triplet qubit, which again corresponds to having now 2 electrons in 2 quantum dots, okay? All right, so the story actually starts from the same point as the 2-qubit gates in the Loss-DiVincenzo qubit. We want to think about having 2 spins in our 2 quantum dots. And remember, we can have 4 states available to us, right? We have our spin singlet, and then we have our triplets, right? And in the absence of a magnetic field, so what this is showing down here is the spectrum of the system as a function of the applied magnetic field that we have here. And at 0 magnetic field, you see that all the triplets are degenerate, right? And we just have the singlet that's split off by the exchange energy J, okay? What you didn't do in a singlet triplet qubit is you apply a relatively large magnetic field, right? Such that these T minus and T plus go far off in energy in comparison to the exchange interaction, okay? And what you then can see is that, well, I have these 2 states left over here, right? My singlet state and my T0 triplet state, okay? And these then are going to be now our computational basis states for our singlet triplet qubit, right? So on our north pole, we'll have the singlet, and on the south pole, we'll have the T0 triple, okay? And then we can think about, well, how does the qubit evolve and how do we control this thing? Yeah. So remember, okay, these are our computational states, and we're going to have a splitting given by our exchange. So analogous to our lost DiVincenzo qubit, right? There was a splitting coming from the magnetic field. Yeah. And remember, that just caused a rotation about the z-axis, right? So here, our exchange interaction allows us to do our z gates. Okay. And then you have to think about, well, how then do I do X gates, right? I need one more axis of control in order to do any type of single qubit gate that I want. And to do that, I need to have some interaction, some coupling between my triplets, my triplet T0 and my singlet, right? And you can do that actually by putting some magnetic field gradient into the system, meaning that the left dot experiences a slightly different magnetic field than this right dot does, right? If you do that, that will cause an off-diagonal coupling between our singlet and triplet, and that gives us the corresponding coupling in the X direction that we need. So now imagine that I turn off the exchange, then my system will undergo normal oscillations about our X-axis of our quantum dot, okay? Now what you should notice here, right, is this acts very much like a charge qubit, right? Where the exchange acts like the detuning, right? Remember in my charge qubit, if I had the detuning very large compared to the time of coupling, I had normal oscillations about the Z. And then if the detuning went to 0, I had oscillations about the X-axis. Yeah, that's the same thing here, except it's just played by the role of exchange instead of this detuning. Okay. And another thing then that's great about this is that there's no AC field to be found at all, right? I can completely change the quantization axis by just slowly varying my exchange interaction between these two dots. So I don't need to take charge and pump it back and forth like we did for the lost DiVincenzo qubit. Okay, so this is kind of the main motivation, just to give you a flavor of how by adding electrons to the system and thinking about, well, how do I encode the information, right? That can allow me to control my qubit in different ways and perhaps get some benefits, right? There's also disadvantages, though, of course. For example, there's now leakage states in the system. So for example, if you end up in the T0 or T minus state, that's called a leakage state, right? Because it's not part of our two-level system. And you're essentially just losing the information then. This isn't such a big problem if you're looking at single qubit gates. But once you put in 2 qubit gates for a single triplet gate, you really have to start worrying about that, right? So there is some disadvantage as well. Okay, so that was kind of the first big part of the talk, just trying to give you kind of the nuts and bolts of some simple operation principles for the singlet triplet qubit. Now I want to talk about the Valley problem for a couple minutes in silicon. And so I'm just going to, really this is going to try and be highlighting a paper that we wrote last year. It's actually 364 days old. I checked yesterday. About trying to solve this Valley problem. And I'm going to tell you what the Valley problem is and everything. But what we're doing here is we're combining two things. We're combining strain in the quantum well along with what we call wiggles in the system. Basically, we're adding these germanium concentration oscillations within the quantum well. So I'll tell you about what those words mean. But even before going there, it was funny. So I was putting together the slides for this a couple days ago, and I was looking at the paper, and it said that it was cited in some Wikipedia article, right? So I was interested, what Wikipedia article is citing this paper. And when I looked what Wikipedia article was citing this is what came up. And I have no idea what happened or how this happened. Indeed, you see at 107, this is indeed our paper being cited for some infantry carrier vehicle dragoon. So apparently this tank has to worry about Valley splitting as well, right? So I really want to know the person that got this mixed up and how this interest overlaps. But anyway, I'll probably never get to the bottom of that, but that's just some fun. So we'll be talking about tanks for the rest of today. Okay. All right. So what is the Valley problem in silicon, right? And for this, we need to look at this diagram here, first of all. This is the band structure of silicon, okay? So here, this is the valence band, and then up here are the conduction bands and we really need to just care about the conduction bands in our system, right? Because these are going to be the bands from which the states of our quantum well and ultimately our quantum dots are going to derive from. Yeah. And it turns out in silicon, the minimum doesn't occur at the zone center, as you might naively expect, but rather occurs at the edge, right, near the X point of the band structure. Okay. And if you then look at this in the full Brillouin zone, it then turns out that there's actually 6 of these degenerate conduction band valleys that are sitting around, right? So there's 2 near the X point, 2 near the Y point, and then 2 near the Z point that are all degenerate with one another, right? And Mark started talking about this a little bit in the question session, but why do you think that having this extra valley degeneracy might be a bad thing, right? What could go wrong? Why might this ruin my spin qubit for me? Yep.
When I'm having different states that can be heard of different things.
Yeah, so I mean, the qubit is supposed to be 2 levels, right? We just want to have spin up, spin down, or in the case of a single triplet qubit, something else, right? But we just need 2 levels is all, right? But now if we have this extra valley degeneracy, we're going to have basically multiple copies of those states, right? So instead of having 2 spin states, for example, I'd have 12 states that I have to deal with, right? And I don't know how to deal with that complication, okay? So the best thing that we can do is try and get rid of those things, okay? And that's what the valley problem is in silicon, is either how do you deal with having the valleys, or how do you get rid of this valley degeneracy? Yep. For sure. So for example, I was just going to show in gallium arsenide, for example, that's a direct band gap, right? And that's basically because there's a gap at the gamma point, right? And the thing is, the gamma point's unique. There's no other equivalent point of that in the Brillouin zone. And so indeed, the values would go away, right? Any other questions? What? Sorry? These 2 states here? Qubits, I see, yeah. So in principle, I guess you could try and make qubits, right, out of these having these multiple states. The thing is, in a qubit, you still need to be able to do controlled unitary transformations, right? I need to be able to rotate within this higher dimensional space in a controlled way. And if I have fluctuations in those energy splittings that I can't control, I would imagine that that's going to be a very hard qubit to control. So that would be one of the main reasons I wouldn't think of that as being a promising venture. Yeah. Okay, cool. All right. So we have to deal with this valley problem in silicon. Okay. Now, part of it gets taken care of for you because there's some strain built into the quantum well. Basically, the silicon germanium in the barrier regions is a little bit bigger lattice constant. And so it's going to take the silicon and stretch it in the transverse direction of the quantum well. And that's going to break the degeneracy a little bit. So while you started with 6 degenerate valleys, that's going to break into now 4-fold degenerate valleys near the X and Y points. And these go up in energy, right? So we really don't need to care about them anymore. This energy splitting is huge compared to any other energy scale in the problem, right? So we don't have to worry about this. So we're left with just 2 degenerate valleys near the Z point of our Brillouin zone, okay? Then these valleys are then their degeneracy is also going to become broken due to some confinement effects in the quantum well. And they're going to split into what's called a ground valley and an excited valley, right? And they're going to be separated in energy by what's called the valley splitting. And this energy valley splitting is an incredibly important parameter when you're thinking about silicon quantum dots, okay? That we would like to be big enough, right? So that we don't have to worry about the valley splitting, right? If it's big enough, then the excited valley, is just some high energy state that never gets occupied. And we can just think about defining a spin qubit within this ground valley manifold, right? The problem is that this valley splitting actually varies from device to device and even from dot to dot. So if you move from this location to just a couple tens of nanometers away, the valley splitting can be completely different and is actually often uncorrelated with each other. So there's a large also energy range over which experiments find. They find that anywhere up to 300 microeV. I wrote here when I wrote the slide, it was down to 20, but now you can actually go all the way to 0. So there are actually regions where the value splitting vanishes. And if you could wave a magic wand and just get rid of this or make the value splitting some value, a nice value to shoot for is to try and get it around 100 micro EV, okay, which corresponds in frequency to 24 gigahertz. Now, the reason why you want this energy value, it's a little bit arbitrary, but this is a good ballpark, is because this is pretty big in terms of temperature. So it's like 100 some millikelvin, which is much larger than what we have the fridge be at, right? And so you won't get thermal excitations necessarily of your excited values. And it's also high in frequency compared to what you normally use in terms of microwaves, right? So it's not going to get in the way of any type of control that you're trying to do if you can get up to a frequency shown here. Okay. The problem is that what I'm calling conventional silicon germanium quantum wells, they very much struggle to get what's called large deterministic value splitting. This is because you need an incredibly sharp interface in order to get this. So let me just explain that a little bit. This is a profile of the germanium concentration as a function of the distance, the growth direction distance in a quantum well. So here, this would be the region where there's no germanium. It's just pure silicon, right? And this is where normally the electrons will live, right? And then there's the barrier regions made of 30% germanium, right? In here. And of course, then there'll be an interface that interpolates between those two values. And this interface has some characteristic width that we can parameterize by a length W, right? And what you actually find is that the value splitting that you get drops off exponentially with this interface width. So you can see here, this is shown that the value splitting that you get from the interface basically goes to zero once the interface is anything above half a nanometer, right? And half a nanometer is only about 3 or 4 monolayers of silicon, okay? So unless you have an incredibly sharp interface consisting of just 1 or 2 monolayers of silicon, your interface is essentially going to give you no value splitting whatsoever, okay? Which you can then ask is, well, okay, I don't get it from the interface, so where does the value splitting come from in the dots, right? They're getting energies from 0 up to 300 micro eV, so where does it come from? And it turns out that it comes from something called alloy disorder. So in the silicon alloy, right, the germanium is sprinkled in at random locations, right? If I have 10% germanium in a layer, there's no structure to it, right? It's just randomly 10% of the atoms will be germanium instead of silicon. And this alloy disorder then creates kind of a white noise potential, right? There's all sorts of different spatial frequencies making up it. And so they'll just happen to be at the right Fourier coefficient, a term that will give you a value splitting, right? But that's why it's completely random. And when you move the dot a little bit, it's going to be sampling a completely different alloy realization. And that's why this value splitting is varying dramatically, right, from dot to dot. Well, that's fine if you just have a couple of dots and you could just move the dots around a little bit. Maybe that's not such a big problem. But if we're trying to scale, to millions of qubits, and we have, a good chunk of them that have low value splitting that are essentially failed qubits, that's going to be a very bad thing, right? And so that's why we would like to have this deterministic value splitting. Oh, and indeed, when you see the pictures of these, the interfaces that they measure are actually much larger than this. Well, not much, but they're about twice. So they measure, you can see it's around 1 nanometer in width for this interface. So it's funny, in the last talk, Mark said, this is a beautiful picture. And you could see nothing wrong with it. When I just looked at it and said, oh, there's something very, very bad with this picture, right? He's not here, so I can say that. No, kidding. Yeah, so there's not going to be essentially any value splitting coming from the interface. Okay, so how do we fix this, right? And this is kind of one of these crazy ideas that you're trying to go about doing to try and solve one of these problems, right? And this is where we introduce what's called the wiggle well, right? I did not name this thing, by the way. So if you think it's a silly name, don't cry to me, okay? It's kind of fun, but anyway. So this is our wiggle well. So what is it? Well, it's very much like a conventional silicon germanium quantum well, right? We have a silicon well here and silicon germanium barrier. But what we do differently is we add a little bit of germanium into the quantum well region, and you add it such that the concentration wiggles in space, right? With some period lambda. And it turns out if you put in the right wavelength for these wiggles, you can have very profound impacts on your quantum well properties, including things like the valley splitting, as I'm going to talk about, but also spin orbit interaction, which I'm not going to talk about here, but it's in these various papers that I've written on this wiggle well subject. And this wiggle well was demonstrated a couple of years ago here at Wisconsin. Okay, this showing the wiggle well of around what we call a long wavelength wiggle well of 1.7 nanometers. Right, it's huge. That was supposed to be a joke. Yeah, so it's demonstrated, and now I'm happy to say that it's actually being grown other places as well. Right, it's being grown at a group in Berlin, Germany, I believe, and they're actually growing this via molecular beam epitaxy now. So you can see the improvement in terms of the growth compared to regular non-MBE type growth shown here. Okay, so why would this wiggle well help at all? Right? Why would putting these oscillations help? Well, the idea was to first put in some ultra short period for the wiggle well. So we remember there's this parameter lambda, the wavelength, and it was shown by Bob Joint, right, who's a theorist here in Wisconsin, a couple of years ago, that if you have a wavelength that's about 0.32 nanometers, you get a valley splitting that's just huge, right? There are some other effects at longer wavelengths over here, but they tend to be quite small, right? And so really this is the one that you would need to do if you're just to do some, what I would call bare wiggle well without anything else on top of it. The problem is that this is very difficult to grow, right? This is 0.32 nanometers for context that's only about 2 monolayers of silicon, right? And so, if you could grow this, well, just make the interface very sharp, and then you could just not worry about the wiggle well at all, right? But okay, this was the original proposal, right? And so we want to ask, well, is there something we can do to the system that would actually allow us to relax this constraint? And what we found last year is that indeed there is, and it's by adding a particular type of strain to the system. So if you shear strain the system, you can actually use what we call the long wavelength wiggle well, right? Which is this 1.7 nanometers. And shear strain is just a particular type of deformation of the system where you are extending the lattice along the 110 crystal direction and then contracting it in the orthogonal direction, right? So this is different than the strain coming from just the quantum well itself, where because you're putting silicon germanium, sandwiching that silicon well with silicon germanium, the whole silicon will expand, but it's uniform in all directions. Here you need to have kind of some anisotropy, right, where it's elongating and contracting, right? So that's kind of the new thing that's being added in here. And if you do this, then what you see is that you can use this long wavelength wiggle well. So this is just some theoretical results showing having a wavelength of 1.7 nanometers as a function of the shear strain in terms of percent, and then also the germanium concentration. And you can see if there's no shear strain in the system, right, corresponding to this red dashed line, there's essentially no valley splitting coming from the wiggles. Correspondingly, if you just include shear strain and you don't include the wiggles, you also get a very small increase in terms of the valley splitting. But as soon as you put these two ingredients together, right, then you suddenly get this large enhancement. And we indeed think for parameters that could hopefully be realized in the lab, we could get around this region here where you see the deterministic valley splitting being larger than 100 micro EV, right? So this is possibly could contend for a way of solving the valley problem in silicon. So then the tough thing is, trying to get the shear strain into the system, right? That's also an engineering task. And so we've proposed a couple of different ways of doing that, which I call 1, 2, and 3 here. The first method is kind of brute force method, where you're just taking this silicon well and bending it, right? It's kind of the caveman approach, I guess, of just bending the system. And this is really just to see if adding shear strain in the system can give you an enhancement or not. We then thinking about etching trenches into the quantum well, right? So what you do is you etch trenches along the 110 crystal direction, and it forms kind of a channel, or we call it an isthmus because we live in Madison, right? And then if you cool the system down, it will contract in an inhomogeneous way, and it will cause shear strain to form in the system. And this is actually a large enough channel where you could hopefully form dots, right, and get this. So this is then more of an intermediate goal. And then in terms of an actual scalable solution, we're thinking about something like this, where you have some silicon nitride stressor that you put on top of the device, and you then etch a trench underneath the quantum well. And the reason for that is because it creates a freestanding membrane, right? You can imagine if you have this huge silicon substrate underneath, the system is kind of like a big rock, right? Where if I try to strain it, it doesn't really budge much. But then if I cut a hole out from underneath the rock, it should be much more amenable to straining it in this region here. And our calculations show that you can get shear strain of very large magnitude over a very large area where you could contain hundreds of dots, right? And so this could possibly be a scalable method of solving the Valley problem. And I just wanted to show there's some really great work from grad students here at UW, and also an undergrad who might be in the MSPQC program now, Colin. Okay, so I guess I don't have too much time to explain this. I'll just give you kind of the big picture reason why it works. In silicon, there's this type of symmetry to the system. So this is a silicon lattice, and it has this weird symmetry. It's called a screw symmetry, where you do this translation and then a screw to it, right? And it turns out that this screw symmetry normally stops the long wavelength wiggle well from giving you the Valley splitting enhancement, right? So if you look at, to try and give you a big picture, this is the silicon band structure, and this is where the valleys are, okay? Now what the short wavelength wiggle well does is it connects these valleys by providing an oscillation that matches this wavelength, right? But this wavelength is very big, okay? And so in real space, that corresponds to something very small, right? This is that 0.32 nanometers, okay? Now, naively, what you think you could do is you could just wrap around the Brillouin zone, right? In type of a Umclamp type process, right? And this is a very short distance, right? And it actually corresponds to the long wavelength wiggle well wavelength, okay? But this screw symmetry screws it up, right? And so what we do is when we put the shear strain into the system, this screw symmetry gets broken, right? And suddenly that pathway becomes available to enhance the Valley splitting with the long wavelength wiggle well. Okay, so that's all I was going to give a little bit more detailed explanation of that. But for the sake of time, I won't go through it. Just very quickly, this is kind of another way of visualizing it. These are the two valleys of silicon. Like I was saying, the short wavelength wiggle well can couple these two guys directly, right? But this 2K naught corresponds to this very short wavelength. When you put shear strain in the system, it causes some dimerization that allows this long coupling in momentum space. And then you just need to provide another pathway to couple these two states, which is provided by these long wavelength wiggles, okay? All right, but just for the sake of time, I won't go through all the details of that. And with that, I think that was all I had. So with that, I will thank you for your time. Take any questions, Gab.
That's not good. You're choosing to get back from pattern or that you're having pattern.
No, that's a very good question. Really, the really reason we put the sinusoidal thing is it's just the simplest thing, right? It's just the simplest thing to analyze. Indeed, there's actually been some work by other groups where they've not used necessarily just a simple sinusoidal, but some other periodic structure, right? And what they showed is that you can actually optimize the ratio of the deterministic versus the alloy disorder, right? So basically, what I mean by that is, let's just go back. Oh, sorry, 1 second. What happened? Let me just go to the thing real quick. Yeah, so you have these oscillations, right? And you need the